Thermodynamics helps us understand the variation in temperature required for the thermal reduction of oxides, and to predict which element will suit as the reducing agent for a given metal oxide. The Gibbs energy is the most important thermodynamic term here. You already know that for a spontaneous reaction, the change in the Gibbs energy, delta G, must be negative. Delta G for any process at a given temperature is given by the equation delta G is equal to delta H minus T delta S, where delta H is the enthalpy change, T is the absolute temperature, and delta S is the change in entropy during the reaction. The change in the Gibbs energy when 1 gram molecule of oxygen is used to form oxides of metals can be plotted against temperature. This graphical representation is called an Ellingham diagram. These plots not only help us determine the relative ease of reducing a given metal oxide to the metal, but also to predict the feasibility of the thermal reduction of an ore. An Ellingham diagram normally consists of plots of change in the Gibbs energy versus temperature for the formation of oxides. An Ellingham diagram for oxides has several important features. Let's look at them one by one. The first feature is that the graphs for most metal-to-metal oxide reactions show a positive slope. Consider a reaction such as the formation of an oxide 2M plus O2 gives rise to MO. In this reaction, the entropy or randomness decreases from left to right due to the consumption of gases. Hence, delta S becomes negative. Thus, if the temperature is raised, then T delta S becomes more negative. Since T delta S is subtracted in the equation, delta G becomes less negative. Thus, the free energy change increases with an increase in temperature, and hence, the plots show a positive slope. The second important feature is that the Gibbs energy changes follow a straight line, unless the materials melt or vaporize. The temperature at which such a change occurs is indicated by an increase in the slope on the positive side. For example, the slope of the ZN-ZNO line changes around 800 degrees Celsius. Similarly, the slope of the MG-MGO line changes around 1120 degrees Celsius. The third feature is that when the temperature is raised, a point will be reached where the graph crosses the line delta G is equal to 0. Below this temperature, the free energy of formation of the oxide is negative. So, the oxide is stable. Above this temperature, the free energy of formation of the oxide is positive. The oxide becomes unstable and will decompose into the metal and dioxygen. Another important feature is that any metal will reduce an oxide of another metal that lies above it in an Ellingham diagram. Thus, Al reduces FeO, CrO, and NiO in the well-known thermite reaction. But Al will not reduce MgO at a temperature below 1500 degrees Celsius. Ellingham diagrams also suffer from limitations. One is that they assume that the reactants and products are in equilibrium, which is not often true. Another limitation is that Although they indicate whether a reaction can occur or not, they do not say anything about the rate of the reaction.